Good morning. Welcome in the Postgres dev room. This morning the first talk was talking about Postgres tuning. That's actually cancelled. The speaker got ill last night. So Shivram was going to do the talk for this morning. So it's about unified frameworks for big data using foreign data wrappers.
Yep, thanks. So, nice to see you all. It's been ages since I've been in a gallery room, and it's the first time looking this side as opposed to this side, so it's kind of weird. So my talk today is about, like as mentioned earlier, it's about a unified framework for big data wrappers. So obviously Postgres introduced foreign data wrappers. So it's based on that framework, but there's an extension that we built, which makes extending foreign data wrappers to talk to the entire Hadoop ecosystem a lot more easier. And I'm Shivram, so I work for Pivotal. I've been at Pivotal for about three and a half years. I've been working on various Hadoop related issues, and then I've just now lately been introduced to the Postgres world through FDW database. So this is the agenda. So I'll initially just start off with introduction to the Hadoop ecosystem. That's like a basic prereq for the talk. Following that, I'll give a rationale as to why we need to have Postgres SQL paradigm on Hadoop. And then I'll jump to what's the current state of SQL on Hadoop, specifically focusing on where do foreign data wrappers exist today, and what are the big data wrapper solutions we have today. Might be critiquing some of them, but that kind of sets precedent as to why we need a new approach. And then I'll be jumping on to PXF. That's an extension framework which we have built, and so that is going to be a proposed solution, and I'll do a short demo if time permits. And finally, I'll just be showing the benefits of using PXF with the foreign data wrapper abstraction. So feel free to just stop me anytime during the talk. I might kind of seem to be running a little fast, but just slow me down and stop me if you want to have questions. If you have questions. So to start off with the Hadoop ecosystem. So yeah, essentially Hadoop is an open source framework which is primarily focused on dealing with distributed data sets on really large clusters of nodes. The point to be noted here is you're dealing with commodity hardware. It's not like the typical like beefy machines that the typical database vendors offer. So you're dealing with commodity nodes. Again, the definition of commodity has changed a lot lately. Commodity back then used to be like 16 gigs of RAM, and these days you find 256 gigs of RAM considered as commodity. But so the word commodity hardware keeps changing over time. Scale out is another important thing. So you need to be able to scale up a cluster from say 100 nodes to 500 nodes and 1,000 nodes, kind of dynamic way. Which also means that if you have a network partition and you lose about half of the data center, you should still be able to tolerate that. So scale out is a very important factor. Fault tolerance as well. And the last, which is not the least by any means, is support for multiple file formats. Like you have various file formats ranging from basic sequence files, text files, JSON, Parquet, Avro, so on and so forth. So that's one of the major premises as to why you have Hadoop and why you have these various tools, because you want to cater to various file formats as well. So in terms of how the ecosystem looks today, this is just the basic components that I've shown. There are obviously a lot more components available today. So at the lowest layer is the cluster file system, that's HDFS. And the basic premise of HDFS, most of you might be knowing, is you have like data distributed on the cluster. You have like typically 3 replicas of data, and it's a simple distributed file system layer. And on top you have MapReduce, which is a compute paradigm. MapReduce basic premise again is you break your computation into simple map tasks, and then you finally group the aggregate results through the reduce step. And HBase is a key value, a NoSQL database, which is a key value system on top of HDFS. So you typically do queries such as you do like faster point queries using HBase if you want to leverage HDFS. And sometimes people break these columns to column families, wherein you can group to similar columns together. So that's HBase. Hive and Pig are the more popular abstractions used today. Hive is essentially a SQL access layer on top of MapReduce. So Hive has pretty much combined 2 different worlds into, it's like a marriage which is not going to last for long. So it's essentially every single SQL query is converted to a MapReduce job. which obviously means like map queries was never meant to be dealing with Hive queries. So, for instance, Hive would never really be used to run like interactive queries. You typically run batch workflows using Hive, even though you have a SQL layer. So, and the compute paradigm is entirely map queries. There's no other paradigm which Hive uses. I mean, there is another offering called this. I'm not going to get too much into it, but we're going to focus on the fact that Hive uses map queries. There's Pig, and then obviously there are top-level interfaces, which are like BI tools and ETL tools, so on and so forth. So that's how the Hadoop ecosystem looks today. So, so in terms of why we need PostgreSQL on Hadoop. So as you see there, I mean, you have various components within the ecosystem, and so the benefits of having a SQL layer on Hadoop are obvious, right? You have this whole ANSI SQL compliant system. You have a very good cost-based optimizer. There's been tons of research done on query planning and query optimization. So you kind of get all of that research, and you can eventually leverage that to work on a scale-out commodity distributed system, namely Hadoop/HDFS. And the support for transactions is huge. I mean, Hive has been working towards it, but you're never going to get there. So support for transactions, which is offered in most databases, is something that could be provided through this integration. And last but not least is indexes. So trying to speed up queries. So so that's the major motivation as to why you need SQL integration with Hadoop. And the way you could actually achieve this is by foreign tables. So Postgres did a great thing, and I think it was kind of long time pending. 9.1 was when foreign data wrappers was introduced. I think 9.1 just had support for read, if I'm not wrong, and 9.3 onwards there was also support for writing data from a Postgres table onto an external table. So through foreign data wrappers, essentially you could write and read data from Postgres to any foreign storage. It could range from a simple JSON flat file, or it could be something as complex as a component on HDFS. So now that we know the rationale as to why we need SQL on Hadoop, so I'll kind of go over what's the current state of foreign data wrappers, and specifically focus on the integration of foreign data wrappers on the big data ecosystem. Yeah. So foreign tables and foreign data wrappers is, it's Postgres' answer to like the external table and the whole MySQL and other databases that are offered. And so I'll quickly go over the primary steps that are involved in actually creating a foreign data wrapper and making use of it. So the first step is you first define a foreign data wrapper. So foreign data wrapper, when you define it, you would provide a handler function. And the handler function is where you actually define individual routines to decide how do you read data, and how do you move from one record to the other, how do you close your data connection, so on and so forth. So I'll get more into the specifics of what it means to create a foreign data wrapper on the next slide, but that's where you define how data is being read from the external system onto Postgres. So once you create the foreign data wrapper, then you essentially just declare the foreign data wrapper that you created above. So you're going to say create extension, in this case Hadoop FDW. Hadoop FDW was something that was already created in the previous step. Once you've declared your extension, the next step is you're going to create a server object. A server object is nothing but you have one server object to deal with one external system. So in this case, if your server object happens to be your Hadoop server, you would define a server object called, just give it any name, and you would say that you want to use the foreign data wrapper called Hadoop FDW, because Hadoop FDW has been created to essentially talk HDFS and Hadoop. And you would provide options. In this case, your options would be your location of your name node and the port where your name runs. So I've just given random values for this one. So this would be what you would define for a foreign data wrapper, namely Hadoop. And if you're defining a foreign data wrapper for something as simple as a CSV file, your options could be different. So it entirely depends on what you're talking to. And the last step is obviously where you finally create a foreign table. So here you would say create a foreign table, you provide the schema information here, you provide the table information, and obviously, and then here you would say that my server information is Hadoop server, and then you would provide options. So in this case, my option here is I'm now trying to refer to the table example real retail history, and this essentially is actually a Hive table on HDFS. because today foreign data wrapper has one foreign data wrapper called Hadoop FDW, and they use that to talk to Hive, HBase, and HDFS. I'll get into specifics more as we go down. So here you would say, I want to talk to this table via this foreign table, and I'm using the following server called Hadoop server. So this is how you define a foreign data wrapper today using what we have at FOSDEM and its extensions. So, and like I said earlier, like when you're defining a foreign data wrapper, you have to have a handler function. That's where you define how do you read data, right? So that's done through these callback functions. So these callback functions, you will implement them in C. That's the abstraction which foreign data wrapper has provided us today. So you would implement these callback functions, namely, like the important ones are like one function where you define your relation size, and then you would define what paths you have to your underlying table. Then how do you read data, how do you scan data, and how do you iterate, so on and so forth. So these callback functions are very critical towards defining how do you actually read data on your foreign table. So once you've defined this foreign data wrapper, and you have a handler function, so you would specify that handler function here, and then you have this means by which you could read data from your external system. So that's what we have today. And so in terms of the existing vendors and existing options which we have to actually talk to HDFS, so there are multiple options available today. So Multicon, BigSQL, and Enterprise DB are three different options, although they follow a very similar idea. So Multicon is, they've done an awesome job in terms of they've provided a very nice abstraction on top of foreign data wrappers, which makes implementing a foreign data wrapper extension a lot more easier than writing C functions and implementing those handler functions. So today you could also just implement foreign data wrapper using their abstractions using Python files. They made writing foreign data wrappers easy, and they have a lot of community contributions to various databases, including Cassandra, S3, and so on and so forth. And there's BigSQL and Enterprise DB, which have kind of similar approaches to building foreign data wrappers for Hadoop. So the approach which they all follow is kind of similar to this flow. So essentially it starts out like this. So if the goal is to create a foreign data wrapper to talk to files on HDFS, this is the flow. So they first create a Hive table, so which is like a prereq. So even if you want to talk to HDFS or you want to talk to a HBase table, their primary requirement is you need to have a Hive table created corresponding to your HDFS or HBase table. So you first create a Hive table using Hive, and then you define your foreign data wrapper like we saw in the previous slide. You define the extension, your server, you define the schema using your foreign table definition. So you have that information done. And then when you actually query, so then when you have defined your schema and then you're actually running a select star, what happens there is it first connects to the Hive server via thrift. And Hive internally would dispatch that when you're doing a select star or you're doing a select star with a filter, that's converted to a MapReduce job. And the MapReduce job internally knows how to group or do aggregation or do filters, so on and so forth, and then finally results a map back to the Postgres table. So as we see here, I mean, there's this primary requirement here wherein everything needs to go through Hive. Like even if you're accessing data on HDFS, which might have no correlation with with Hive as such, you still need to create a Hive table and map that table, essentially use that table to access from Postgres to HDFS. And the access is done using MapReduce. That's what all these three systems provide today. This is clear because this understanding is kind of essential towards knowing why we need a new approach. So in terms of the way the flow goes is when you're doing an access from PostgreSQL using foreign data wrapper, it uses thrift to talk to Hive server. And so if you have a file on HDFS, you first have to load the HDFS file onto Hive as a table, and then you use the foreign data wrapper extension to talk to HDFS. Similarly, if you want to talk to HBase, you need to have a Hive map table on HBase. You need to have HBase map table on Hive, and use that table to essentially access table data from HBase. And internally, when you're doing filters and when you're doing like joins or aggregate functions, or if you're using a Hive-based function, that's all now going to be converted to a MapReduce job. So as you see here, the primary requirement being here is Hive, and we also know that Hive isn't the most it is functional, but it isn't the most performant system, primarily because you have everything is converted to a MapReduce job. So if all that you want to do is something as simple as just simply read 100 records from HDFS, right? So I'm still forced to create this Hive table to access those blocks. Same with HBase. I'm unnecessarily now have this requirement to create a Hive table that maps to the underlying HBase table. So that's how all the providers, this is the means by which the big data wrapper extensions are written today. So I'll now move on to a slightly different approach. So we built this product called Extension Framework. P stands for Postgres, or if you have any, we started out naming it as Pivotal Extension Framework, but we're still debating as to what's the right name to give it. So I'll go through the design and architecture in terms of how we have decided to tackle the same issue. So yeah, so brief. So currently PXF is offered only in Hawk, but we do have plans to make this a top-level project and also have this entire product available to the Postgres community. So just a brief introduction. Hawk is an MPP SQL engine on HDFS. There's also going to be a talk on Hawk on a different dev room today, so if you're interested, feel free to go there. So that evolved from Read From Database, which is an MPP SQL engine on, it's an MPP SQL engine. So PXF is an extension framework that allows Hawk to query data on external unmanaged data sets. It could be data residing on Hadoop, HBase, or Hive. So today we have a bunch of built-in connectors to all those data sets, and we also provide an extensible means by which an external developer can just simply plug in. An external developer can plug in his code and have his own custom connector to his own data format. It could be something as simple as JSON, or it could be a connector to a Cassandra database or Parquet file. So in terms of how the communication works today for PXF is a Tomcat, it's a web app that's written that uses Tomcat today. And the way communication happens to PXF is through REST APIs. So once you define an external table in Postgres or in Hawk in this case, and then you first talk to PXF using the web app, and then we have a bunch of Java APIs to directly talk to Hive, HBase, and Hadoop. So like you see, you completely remove Hive from the actual path which is needed to talk to Hadoop and HBase. The advantage you get with this is you have a faster way of actually accessing blocks of HDFS. You can directly stream data from HDFS onto the underlying SQL engine. So we have these Java APIs implemented and a few more. There's not enough space to mention every single thing. And then this is the regular native flow where Hawk directly talks to HDFS. So the talk isn't going to be focused on this thing. We're just primarily focused on the external table and the PXF approach of accessing data in the Hadoop ecosystem. So in terms of architecture, you have PXF agents deployed throughout your cluster. So say you have a cluster wherein you have your name node and you have a bunch of data nodes, and then you have your segments, which segments are like, consider them to be like Postgres or Hawk segments wherein you have each agents of Hawk running on each node, and you have PXF agents running on each node as well. And each PXF agent is responsible for fetching blocks from the underlying data node on Hadoop on that particular node. So once Postgres or Hawk wants to make an access onto HDFS, it would, and if it finds that the block of data resides on, say, DN data node 2, it would dispatch the call to the PXF agent on data node 2, and PXF agent there would figure out how to actually read data locally from the underlying node, and it would stream the data back to the master. So that's the architecture in terms of how it's laid out. And like I said, it's not, you don't need to have PXF installed on all data nodes, although it's recommended because you have locality in terms of it's much faster if you have an agent that queries data directly on the local node as opposed to having an agent from here access data from a remote server and then that one stream it back to your client. So that's the architecture of PXF. And in terms of the flow, so you have 3 steps. I'll just break it down into 3 simple steps. You have a fragmenter, you have an accessor, and you have a resolver. So fragmenter is where you would say if you're trying to access data on HDFS, so that's where you would say essentially your goal here is to partition your entire data and you want your locations of each partition. So if you're dealing with say like 100 gigs of data and then you break them down into individual fragments, in the world of HDFS it's going to be blocks. And your fragmenter, at the end goal of your fragmenter is you want locations of every single data block on HDFS. So in this case it would be which node it is, which location it is, what's my block ID, so on and so forth. So once you've fragmented your data and you get the address for each fragment, the next step is obviously you would need to know how to read and write my individual fragment from the external location which the fragmented is provided. So that's where you build the accessor. And accessor is where you actually define how do you actually read and write an individual fragment from HDFS. So all these individual components have to be built for the corresponding subsystem that you're trying to access. So if you're building a plugin for HDFS, you build a fragmentor, a means of splitting, a means of accessing for HDFS. If you're doing a similar thing for Hive, you would build all of these three for Hive as well. So for any custom data provider, you have to build all of these three. And finally, the last step is resolver, wherein, so once you've accessed, so at the end of accessor, you would be reading and writing your data from the external system. And those would be converted to individual records. But just having records from HPS, Hive, or HDFS doesn't really make any sense unless you know how to map this record to a Postgres record or a record which your SQL engine finally understands. So that's where you build the resolver when you're saying, this is the way by which I map a record from system A to system B. System B in this case is your SQL engine, and system A could be any custom data provider. So those are the three steps. So, and if you want to compare in terms of the DDL language, which we kind of saw earlier on the foreign data wrapper world, and use that and show a corresponding example in terms of how PXF defines them today, it looks like this. So, today with foreign data wrappers, you first initialize the extension that you define. So, if you have a foreign data wrapper called Hadoop FDW, you first initialize that, and here you have something wherein on the SQL engine you would say create protocol PXF. And the place where you define you're creating a server object for your external system. So in this case, you're defining a server object for Hadoop foreign data wrapper with the name node and name node host and address. And corresponding to that, so it's all done within the steps. So here, what you do is you define this external table on your SQL engine. So and then you define the schema here. So the schema information is very similar to the schema information that you provide using foreign table definition there. So that's mapped to that. And the location that you provide here would say, hey, I want this external table to essentially map to this particular location. Here I would say this is corresponding to the name node which runs on this address and this port. So that information could be mapped to the information that you specify in the server object. Although the port numbers don't map, but it's supposed to map. And here you would say, okay, now I want to be using this location. I want to be accessing this file. So in this case, it's a Hive file. I'm saying I want this Hive file, which is the database for example, and the table named reader history. And that is going to be mapped to, so you have that information available as the option when you're defining a foreign table there. And what you see here is this is the additional things that we provide. Like in the foreign data wrapper world, there's one foreign data wrapper implemented for Hadoop as such. And internally, it uses the same paradigm to access data irrespective of whether it's on HDFS, Hive, or HBase. But here we have a clear distinction. So you have a separate profile. So if you wanted to access HDFS, you would say profile equals HDFS. In this case, it's a Hive table, so you would say profile is Hive. And with HBase, you would say HBase. So the main goal here is you want to have completely different approaches of accessing each of these systems. So that's one fundamental difference that we have here in terms of how your specification flows. So your time set. Is this clear so far? I mean, if there's any questions, feel free to stop. So there's a slight difference in terms of how the table is defined here. And in terms of how the data flow goes, like when you're running a select on your external table, like so in this case you define the external table here, right? So once you do a select, what happens first is it first sends the query to your master node. Like I said, since Hawk happens to be an MPP engine, you have a master and you have segments. So it first sends the query to a Hawk master node. And so there it essentially sends the query. The first request is sent via a REST API to PXF. So there's a PXF agent running on the name node. So the first call obviously is to fragment your underlying data. So you would say first get me the fragments for my underlying data set. So the call is sent to PXF. And then now PXF knows how to partition your underlying data. So in this case, it's HDFS file. PXF talks to name node and figures out the fragment partitions, and it gets the addresses from the name node and returns the response via JSON back to the Hawk master node. So essentially now we have partitioned the data into individual blocks, and we have the address of each individual block. So once the data is sent back to the master, there's a kind of a sophisticated algorithm that happens here wherein it decides, like say if you have 100 nodes on your cluster, and if your fragmenter happens to have like 5 blocks, happens to have like say 30 blocks on 30 different nodes, and given that we have blocks which are replicated, we'd have 30 into say 3. So there's this mapping algorithm that happens to figure out what's the best way to parallelize my access onto the segment so that I get achieve as much throughput as possible. Like I don't want to access 3 different blocks from the same node because I'm kind of throttled by the bandwidth I have from this node to that particular node, right? So my goal is to achieve as much parallelism as possible. So I'd as well use the replica which is located on a different node. That way I kind of leverage more network bandwidth. So I map the given fragment locations to the corresponding segments that I have. So once this is done, then I finally send my query dispatch to the segments. This is done by a UDP interconnect today. So once this dispatch happens, and now the hawk segment gets the call, and then it's now delegated to the peaks of agent that runs there. And then it runs the accessor. Accessor is where it actually reads and writes the underlying fragment from the local node. So the peaks of agent would now invoke the accessor class that it defined. So it now reads the fragment into individual records. And once the record is read, it's now passed through the resolver class, wherein the individual record is converted to a record which your SQL engine understands. So that's the last step, wherein the data accessed by the accessor, which happens to be a record, is mapped to a Postgres or a Hawk record. And finally, those records are streamed back to your master node. So that's the flow in terms of how it goes via peaks. So essentially, the 3 steps here: you partition your data, and so that you have individual blocks that could be accessed separately. You access them, wherein through your accessor, those are converted to records, and those records are now mapped to your underlying SQL compliant record, and those are streamed back to your Hawk master node. So what do we have today with peaks? So essentially, you have the profiles that we offer today, which are built in, are as follows. So there's support for HDFS, Hive, and HBase. And it's not just that, we have support for multiple different formats. So like I said, in the Hadoop ecosystem, we have various formats, right? So I haven't mentioned all. So you have text simple, you have support for text multi, support for Avro, there's also support for Parquet that's been added. And you can also access JSON files, CSV files, so on and so forth. Because a user is free to define his own format and define his own delimiters. You can access any sort of file from HDFS. And the beauty with Avro is we also have ways by which you can map a given Avro file to a corresponding table in many different ways. So I don't want to get too much into the specifics, but it's not something as simple as just stream an Avro file and create one single table. You can define the way the underlying Avro data is actually converted to a table. So, and similarly with Hive, we have support for multiple formats. And what I mentioned here is today we have support only for read with Hive and HBase, whereas with HTables we have support for both readable and writable external tables. So outside of that, we also have this plugin based model wherein so we have custom profiles provided, and since essentially you just need to have 3 classes implemented, right? Fragment, access, and resolver. So we have base classes in the community, you just need to implement these 3 classes to have their own plugin defined for a custom data source. So we have many community driven plugins. Today there's support for Cassandra and Akimbo. And support for JSON just got added. I just have a pull request recently. This was done like a couple of days back. This is to support JSON with more complex formats onto a table. So there's a lot of community adoption as well today. So yeah, I'll just jump to a demo just to see how the whole thing, how do you see the whole thing from end to end. So just give me a few minutes. Okay. So all right, so I have three tables as you can see here. So there's 3 simple tables. These happen to be external tables. You have one table called transactions, which is an external table to HDFS. So I'll just blow out the schema. Yeah, so this is an external table. Oops. Yeah, as you see here, this is how it was defined. So I'm now saying that this table called transactions corresponds to the file on HDFS, which is peaksofdemo/transactions.csv. And my profile is HDFS simple, so which means this is a HDFS file. And I've also defined my delimiter, which is comma, and have a bunch of other options defined. So if you want to look at the corresponding SQL query which I actually had to use. Yeah. So here, what I'm defining here is I'm defining an external table with my schema information, and giving my location, which would have the name nodes, location, and the port, and the path of the HTTPS file I want to access, followed by the profile name. And then I'm specifying my the format of my file. So in this case, it's a CSV with a delimiter comma. So now that I've defined this table already here, and I have this file here. So, and I have two more such tables. I have one for, there's a products table which corresponds to an external table on HBase. And there is a customers table which is an external table on Hive. So I can show you the corresponding schemas just to make things more simple. So the HBase table is pretty similar. You map your HBase fields here and you define the data types. So I have four fields here. A record key is something which you always need in HBase. It's a root key, because it's a key value system, you always have a key. And your values here are your fields here. So you have a name, you have a price, and you have the category here. So this is a product table which maps to HBase table. And I've defined my profile as HBase type. So, and the last one is I have a customers table, which is an external table on Hive. And these are my fields on the Hive table. So, and I've defined my profile as Hive. So now that I have my three tables defined, so I could kind of run like very interesting join for these, or I could just run like, say, if I wanted to do something like, just look at an example. Okay, so this is one query wherein, what am I trying to do? So I'm trying to get the top 5 purchases by country. So the query isn't too interesting, but what's interesting here is I'm now having a predicate called country equals Belgium. And like I said earlier, the customer information had the country field, and the customer information was a table on Hive. So I'm having this predicate called country equals Belgium, which would eventually be pushed down to Hive. So there is support for predicate push down. And then I'm obviously joining it by the transaction table. So I have my transaction table where every single transaction done by a customer is logged on. And then there's customers table which has customer information, and then there's products table which has product information, such as what's the price of the product, what's the category of the product, so on and so forth. So here I'm interested to know what's the top 5, what are my top 5 purchases done by this one. Oops. Okay. This always happens on a demo. Okay, so looks like my Zookeeper instance is down, so let me just quickly restart this. So hopefully things should work now. If it doesn't work, yeah, you could throw eggs on me. Okay. So now group my purchases based on product names. So now I know. These are actually. The data sets that I have are Jersey sales, and these are my transactions. So apparently Morgan and Abbey Wambach are the most popular purchases. Again, it's a very, very, very small data set that I've pulled because I'm just running this on my Mac. So essentially what I have here is I've joined my transactions table from HDFS, and I'm joining that with my product table on HBase and my country table on Hive with a predicate called customers equals Belgium, which is pushed on Hive. So now let me, so I'll have another query wherein, in this case I have a predicate called product price less than 50, so I want to push this predicate down to HBase because my HBase table is the one that actually stores the product price. And nothing too interesting, I'm just showing the total purchases done below the price 50, and say I have 5 customers here. So these are the total purchases done in terms of total revenue provided by users, as long as each transaction is below 50. I mean, it's not a very logically great query, but the goal here is to show the fact that we push down this query down to HBase. So, so you have support for HBase and Hive. And the last one which I wanted to show is, okay, so the one part which I missed so far is support for write, right? So, like I showed earlier, we have support to create writable tables onto HDFS. So, so let me show you the schema which I have for the table created. So in this case, I have a writable table, writable external table called customer spend. And here I have my customer name and total as 2 fields. So I'm going to create this table. We don't have any such table or file pre-existing. And the location where I want this table to eventually get into is pxfdemo/customer spend. And my profile is going to be HDFS text simple because it's just a flat HDFS file with a CSV file with comma separated delimiter. So now that I've defined this table called customer spend, which is yeah, so I have this external table defined on my SQL engine. So now I'm running my query, which is essentially what I'm doing here is I'm just selecting the first name and last name and the customer name, and I'm summing my product price and I'm applying this filter. So it's some interesting query that basically joins HBase, Hive, and HDFS. And oops, I was looking at it wrong. Yeah. So there's some select query that happens below. The more interesting part is I'm finally trying to insert that into the customer spend table, and obviously I've defined the profile earlier through the schema. So once I run this, so I have 329 records inserted onto HDFS. So we can just go have a look and see how my data looks. pxf_demo, and the folder name is customer spend. So it spits them out as individual files and it flows every single file. Each file is kind of restricted in size. So you have individual splits here. And the final data is now written through a writable external table onto HDFS. So I just ran these queries to demonstrate like very basic functions that we have to demonstrate like what kind of features we support onto HDFS, Hive, and HBase. Okay, so now that we have this brief demo, so then feel free to just look up my demo data is here, and I have my GitHub location of the pxf source code at the end of it. So now if you pull this entire pxf layer, and the goal here is to not so specifically talk about what we have at pxf, but we want to eventually leverage this pxf paradigm and get an entire paradigm integrated with foreign data wrappers. So that's the goal, and the obvious advantages you see is you get a much more faster way of talking to the underlying Hadoop ecosystem. And what you would need with here is you obviously, somebody wants to integrate pxf with foreign data wrapper would have to implement these callback functions to essentially use the pxf APIs, the REST APIs. So that's the only work that needs to be done. And we already have a library called libcurl, which is a much more optimized libcurl version, which is a very fast way of just talking REST or any network API. So you can just leverage that to implement this one. That's the only pending work required to integrate pxf onto PostgreSQL via FDW. So last but not the least, I'll just go over the benefits of what you get by marrying these two different software. The first thing is you want your foreign data wrappers to be completely isolated from the Hadoop ecosystem APIs. Because, I mean, your APIs from the Hadoop ecosystem is going to be complex and we have various different versions. You want to keep them as isolated as possible, and pxf offers you that. And the most important thing is you have direct access to HDFS blocks. So I don't need to have a Hive server running. I don't need to have a very complex component running. If all that I want to have is Postgres table talking to HDFS files. You get a lot more fast access, especially when you try to short-circuit access onto local file system. You don't even need to read data through HDFS. You can also read directly from the file system. So, and then you don't need to access, you don't need to leverage Hive's underlying execution system. Hive uses MapReduce, so you don't really need to use MapReduce for running like group by or filter queries. You can as well get them filtered on the Postgres side. So you're not forced to use the MapReduce paradigm which Hive offers today. And similarly with HBase, I don't need to have a table on height which maps to the HBase table. I could directly access table on HBase. And PXF offers obviously support for single and multi-input, because the demo that I showed you was for PXF to work with an MPP engine. So if Postgres were to be extended to support multiple nodes, you could still leverage PXF to just work out of the box. Extensibility and ease of building extensions is something which I have to really highlight, because we have had a lot more size, number of records, so on and so forth, and we populate them into PG stats or the necessary PG tables. So that's done when you run analyze function, and that internally calls the PXF API, which we connect them. So did that answer your question?
So you don't, essentially you don't make a foreign network call in order to
Yes, because the data is available local, but yes, when you run analyze, there's a network call happening, but that's one time. And typically you don't keep running analyze too often. You run it once and it doesn't have to be entirely accurate, but you get a decent synopsis of all your data.
Can you show actual explained plans of the queries we were doing?
Sure.
Please.
Any specific query?
Just any.
Yeah. So this query was, I get a simpler one. Okay, so this is a query wherein I group by Belgium the top 5 purchases. Okay, so yeah, the first part is where we segment the query into the segment because it's an MPP engine. So was there anything specific that you want to look at this? Or?
The interesting part is where predicate is pushed down to the customer framework and any new added plan nodes. I mean, non-standard plan nodes, which are interesting.
Okay. We can talk about this offline.
Any other questions?
To what extent does this overlap with the work being done for parallel query GAN aggregates in 6 in terms of the use of infrastructure and getting the ability to use this stuff into core?
Yeah, so the goal of PXF as such is not so much on the notion of the parallel segmentation of the query. That's a completely different product. So you could still take PXF, and if you have Postgres to support a parallel query access, you could very well leverage PXF to break down your query, your underlying blocks to fragments and access them. So this PXF is specifically focused on external table data. PXF doesn't have any smarts as to how queries dispatched from a master node to segment node, so on and so forth. All of that will still have to be done as part of Postgres. So if you take PXF and run it on Postgres, we don't have anything to actually parallelize your query. What we do is we allow you to use your parallel SQL engine to parallelly access data running residing on an external system.
Any more questions?
Cool. Thanks a lot. So feel free to just stop by and